So I'm going to start a new subject, which is one of the coolest subjects. Sort of introduction to gauge theories, especially in QED and QCD. As you're going to see, it's a very deep and heavy subject. You should only scratch the surface. You see some nice parts around. Okay, but for that, another short introduction, mainly a reminder of you for things about the Lagrangian formalism, because we are now going to use the Lagrangian formalism. So even before that, do you have any more? Okay. So remember, we have basically three layers. So the first layer is classical mechanics. And in classical mechanics, we treat particles as point-like functions that evolve in time. Okay? If it's a rigid body, it's a combination of points which have some connection between them. Right? And the way they move is given by the equation of motion, which is Newton's second law. Right? Points like particles. Then we have Newton's second law, F is equal M x dot. Right. Then the next layer is quantum mechanics. Right. In quantum mechanics, the particles are no longer point-like, but they are waves, right? Particles described are described by wave functions, typically denoted by psi. Okay. And they obey a differential equation which follows from the kinematics. Right? So it's the spin. Right? That can be Maxwell's equation, Dirac equation, Schrödinger's equation, depending what we do. And then the particle nature of the particle, we say that when it has some interaction. Only then there is this collapse of wave function into a certain location. So only when we try to make a measurement, namely we ask the particle to interact with something else, then we say that it's actually a particle and not just a wave. Right? The particle equation of motion is derived from the kinematics. And then the particle nature of the particle is seen when it interacts or being detected. The third level, which is really the level that we are working on, is called the quantum field theory. Quantum field theory. UFT. And then the basic entity is not a particle anymore, but now is the field. Which is a basic entity. Which, again, fulfills a certain differential equation. Yeah.
Do we differ in classical mechanics between Newton's law, Newtonian mechanics, or Lagrangian mechanics?
No, it's the same thing. Lagrange is just a different formalism. Yeah. Lagrange, Hamilton, Euler, they're all 19th century. Euler, I think 18th century. They are all same formalism with the same idea. It's not a different conceptual idea. It's a different formalism. In quantum field theory, the basic entity is the field. Right? The field also obeys a certain differential equation. There is a certain differential equation in which the fields evolve according to. Particles, what we call, are excitations of the field. Particles are excitation of the field. What does it mean? We think of a field as a quantum operator that acts on a vacuum, right? And this quantum operator can create particle or destroy particle. It's analog. It's actually the formalism is the same as the simple harmonic oscillator in quantum mechanics that you've seen. You have this raising operator and lowering operator. So it's the same idea. Every field is made of operators, but instead of raising energy levels or lowering energy levels, as in the simple harmonic oscillator, they're exciting. This excitation we call a particle. Okay, so it's a different concept, but it turns out to be work. Right? Fields are quantum operators, are made of. They are made of quantum operators that create and destroy particles. Of course, the advantage in quantum mechanics, we cannot create particles and we cannot destroy particles. Particles are just there. Right? There's no concept of a particle that disappears. The wave function has to be normalized to 1.
Don't you have atom absorption? Or it's,
photons.
Photon,
Yeah. Photon, yes. But not the electrons and positrons. You don't have that. When there are interactions are described by multiplicity of operators. That create some particles and destroy others. Right, so that's the key difference, right? The whole idea is that we need to have some formalism to enable us to change the number of particles and the type of particles that they are. You start with one type of particles and you end up with a different type of particles. Right, classically now we can think of electromagnetic field. Ground state, there is nothing. First excited state, that's photon. Second excited state, 2 photons, etc. So basically for every particle that we have in nature, there is a field associated with it. Okay? That's the basic concept. Right. The way to describe the physics or the model, right, which means the type of particles and their interaction, is via the Lagrangian. Now you can think of other ways, but this is the standard way. And the most comprehensive Lagrangian there is the Lagrangian of the standard model, which takes a whole page. If you want, then at the end I can show you this. You'll see that after this, at the end of this, not this lecture, at the end of the semester, I'll show you some, if you want, I'll show you the Lagrangian, you'll see that some parts of the Lagrangian you understand, some parts we didn't have time to discuss. We will not have time to discuss. So the Lagrangian gives all the information about, so the model, maybe here. So in the model, right, then we have a Lagrangian or a model is described, model such as the standard model, right, is described by the Lagrangian that contains all the information about what types of particles. So if we are to discover a new particle, we have to add a term to the Lagrangian. What are the symmetries? And two, the symmetries. And that is the key point. That is, in fact, what the message I want to deliver in this subject. Here is the fun part. All the interactions within the model are described by the symmetries of the Lagrangian. Okay, take you a second to digest that. That's an idea by Hermann Weyl, a mathematician, which actually proved it in some parts. And to the best of our knowledge, it works. And I'm going to show you how it's going to work, and that's really going to be fun. Okay, symmetries, they describe interactions. And that's the origin of these gauge theories. Yeah, I mean, some things we saw, right? From the Lagrangian, we can derive these Feynman rules, which will tell us measurable quantities, such as decay rates and scattering amplitudes. What else we have there? Right. So, as I already said, every new physics that will be, the meaning of a new physics beyond the standard model is to simply add terms to the Lagrangian. These terms will describe either new particles that we don't see, like supersymmetry, and how they interact with the known particles that we have. That's what we do. Yes?
In the Lagrangian, we don't see any type of, we see the masses of the particle?
We put them. These are free, you'll see it. Let's see some terms, right? Like we have in the Dirac equation, we have a mass term. So we put a mass. But we don't, the Lagrangian itself, the symmetry does not tell us what should be the value of that mass. It will tell us what interactions this particle can have. Okay? So this is a free parameter of the model. Yes?
כל חלקיק יהיה לגרנג'יאן שלו, או יהיה לך אחד שכלומר...
There will be one Lagrangian that describes all the model. The model describes all the particles and all the interactions between them. So if we discover tomorrow a new particle, that means that there is some term in the Lagrangian that is missing. So people will start running. Well, they already do that, right? All theories of supersymmetry suggest that there are additional particles which have a certain interaction, and the way it's being described is by adding more terms to the Lagrangian. Okay?
למה זה דווקא אבל חיבור שלו זה קומי?
The Lagrangian described the model itself. And the model contains everything we know about particle physics. Everything we know means these are the particles that exist in nature, to the best of our current knowledge, and these are the interactions that happen between them. That's all. So we managed to take everything we see in particle physics, squeeze them into one big formula, one big Lagrangian, and that's it. If we discover new particles, if we discover new interactions that we don't know of, we'll have to modify this Lagrangian. Okay, that's the idea. What I'm going to show you now, I'm going to have a short review about Lagrangians, and this is not the Lagrangian that you saw in classical mechanics because it's a quantum field theory, so I have to introduce to you exactly the differences. It's not that different, it's not that difficult, but you have to pay attention. And then I'll mainly describe this idea, that the symmetries in the Lagrangian describe the interactions. That's the main thing. This is it's quite deep, but it's quite deep. Right, so yeah, so of course if you really to understand everything, we need first to understand quantum field theory, which we're not doing, so I'll just tell you, and these are the parts that you have to trust me something. Okay, questions, more questions. So as a quick reminder, and I understand that there are some people who did not take Lagrangian physics and Lagrangian mechanics course. Okay. Well, I'm like, okay, so then we'll go over briefly, just as a reminder about Lagrangians in classical physics. It's a second-year course in physics. Quick reminder, take 10 minutes, not more than that. We're going to spend the time. Right, so we can write down the equation of motion as Newton's equation of motion, and we can do it equivalently. We can do it in a different formalism, which gives us a much stronger tool. Namely, it's easier to solve more difficult problems by defining the Lagrangian L, which is a what? Why is that not working? What is a Lagrangian?
Kinetic minus
Squared.
T
minus u.
T minus u, right? So L classical mechanics. L is T minus V. What is T? Kinetic energy. What is V? Potential. Why is none of my fans working?
You need a
Unrelated question.
Right.
Sorry? So T, kinetic energy. V, potential energy. Right? And then Lagrangian itself, L, is a scalar function of
Q.
the general, what is Q? L is a scalar function. What is a scalar function?
Its output is a scale.
Output is a scale, right?
Yes.
Think of it the following. Temperature, right, is also a scalar function. So that means that it's a function of the volume. In every point, I can take a thermometer, right? I can tell you what is the temperature at each point in this room or everywhere in space here, right? That is a scalar function because I get a scalar result, right? If I measure the electric field, for example, I will get this is a vectorial. It means at every point, I'll get a vector. T, I'll get the scalar. L is a scalar function of the generalized coordinates. Is that right? Of the generalized coordinates and their first derivative and their time derivative. So L is L of Qi and Q dot I.
What about space-time?
That's classical.
If you have a potential which is changes it over space.
Yeah. So Qi.
But can you depend on
What's the difference between generalized coordinates and standard coordinates? Cartesian coordinates?
those who have any length? Do you have?
Yeah. That this is what is best for me. Right?
Or does it contain time?
L? Ah yeah, there is a time, but I will. Yeah. Because I don't. Yeah. Omit, direct, is dependent. So once we know what is a Lagrangian, how do we get in for the equation of motion? Euler-Lagrange, right? So Euler-Lagrange equation of motion. Which is d over dt, right? dl over dqi dot is equal to dl over dq I. Note, this is a partial derivative, this is a full derivative. Go with me? That's equal to the equivalent to the equation of Newton's second law, and it really comes from originates from what we know as the principle of least action. Another name for the principle of least action? What? Hamilton's. Yeah. So the Hamilton's circuit.
Fermi's for only photons?
Yeah. Hamilton. You've seen it, right? I'm not telling you news here. But it's Hamilton's principle. Which says that we can, using the action, right, S, which is defined as S, is an integral from T1 to T2 of L dt. And then delta S, change in S needs to be 0, right? So delta S is delta of integral from T1 to T2 L dt must be equal to 0. This is the principle of least action. And then delta L, or we can switch the order, right, of integration and the differentiation here, and we can write that as integral T1 T2 of delta L dt is equal to 0. And delta L of Qi and Qi dot is the L over d Qi, and delta Qi plus the L over d Qi dot, delta Qi dot. And then integrate by parts. Use the fact that delta Qi and delta Qi dot on the boundaries are 0, right? Use delta Qi at T1, actually it's only delta Qi. Delta Qi at T equal T2 is equal to 0. And we get delta S is equal to integral from T1 to T2 of dl over dqi minus d over dt of dl over dqi dot delta qi dt is equal to 0, and voila, just prove you the Euler advantage equation. Yeah, we've seen all that. Example. Example 1b. Example 1b. What do we have? So let's say that L equal T minus V, so let's write it as half mx dot squared minus V of x. V is the potential. So dl.
So the potential doesn't depend on the derivative?
No, so dependent derivative, yeah. dl dx dot. Max dot. Right. dl dx. Minus dv of x over dx. And Euler advantage equation. x dot dot is equal to minus dv of x over dx.
If v is only dependent on the x coordinate, so it's a real derivative. It's not a partial derivative.
Yeah, it's 1d. It's a 1d, you're right.
Yes.
It's because it's a 1d. Okay, we can do the same for a little bit more complicated Lagrangians. Do you need me to do that, or does anybody need? Don't be shy. Okay. What about quantum field theory?
It's really
Now it's the same, nearly the same. But conceptually it's the same. Can I erase that? Erase that? Okay. Lagrangian and QFT. So, in classical mechanics, the Lagrangian was a function of a finite number of discrete parameters, qi and qi dot. Right? So, classically, L is a function of a discrete number of generalized quotients. Now we said, what is the basic entity in quantum field theory? It's a field. And the field is continuous. It's everywhere in space. Okay? So, similarly, when we talk about the energy, for example, of the field, this is a continuous function of space. Right? So there's no discretization. Okay? So, in QFT, generalized coordinates are replaced by continuous fields. Continuous outside, right? So, in QFT, that means that as opposed to classical mechanics, that's the key difference here, that the dynamical degrees of freedom in QFT, the dynamical degrees of freedom are the values of the fields. For example, phi, just an example, right? At every point in space-time. So the real issue is to extend the Lagrangian for continuous systems, not for discrete systems. Okay? So to do that, we introduce the concept of a Lagrangian density. Okay, so we introduced, so to incorporate the Lagrangian formalism, we introduce what's known as the Lagrangian density, which is denoted with a curly L. Like that. So, rather than, and of course this is going to be a function of the fields and of their first derivatives. So L is equal L of phi and d mu phi. Phi I, because it could be many fields. Okay. So rather than L of Qi and dQi over dt, now we're talking about the Lagrangian density of phi I and d mu phi I. Clear? Make sense? Just that you know that at a certain point people simply forget to say Lagrangian density, it's just a Lagrangian. So in the form, when we speak about Q of t, when we say Lagrangian, it's likely going to happen to me as well. When we say Lagrangian, we really mean Lagrangian density. Okay? So that's sort of a curly L you can practice on how to write it. What is the Lagrangian? Not Lagrangian density. What is the Lagrangian? What's the relation between the Lagrangian and the Lagrangian density?
The integral over
the 3 space. Okay, so L is integral of L d cube x. And the action? Integral over
entire space.
Right, space and time. So S is integral from T1 to T2, right? dt integral L d cube x, which is simply integral L d4x.
Wait, you say d3x, how isn't it dq, d3q?
Space, the entire space, it doesn't matter.
So what is x? מה זה q ומה זה phi, מה זה x? כאילו מה הקשר בין phi ל-x?
Okay. Phi is a field. L really depends on the values of the fields in every location. The fields depend on the space-time. They evolve in space and time. Okay? So if you want the total Lagrangian, we need to take the Lagrangian density and integrate the value of the Lagrangian density over the entire space. Everything makes sense, it just takes a little time to adjust. So the action is integral over the 4 volume of the Lagrangian density. Good. And you know, by doing that, we can actually, what I just showed, that we can take the action and fit it into this formalism of the relativistic theorem. Okay. Yes. All space, infinity. Okay. Everything. I don't know, minus infinity to infinity, but you know there should be 3 integrals. Okay. Now we can write down, you know, I just derived to you Euler-Lagrange's equation from Hamilton's principle, right? Principle of least action. It was a good reminder, but that we can now repeat the same steps and re-derive Euler-Lagrange's equation in the quantum field theory formalism. Okay. Let's do that. Do it here. Questions about that? Should be straightforward, but things are getting confusing. Yes?
We use the הנגזרת הווריאנט.
Yeah. Here?
כן. אז אנחנו עושים אינטגרל רגיל על כל המרחב, או צריך להתחשב במטריקה?
רגיל. Forget now about curved metrics. Right? But you mean, it doesn't matter, right? I do here, I can do it in spherical coordinates. If you mean spaces which are not Euclidean, that's a different story. Forget it. And for this course in general. This is integral over the entire space. Okay. So now let's write down the Euler-Lagrange's equation for QFT. So, principle of least action, delta S is equal to 0. Questions, guys? It's fine. I'll be surprised if there are no questions. Is a what? Is the integral delta L d for x. So it's integral, right? L we said is a function of the fields and their derivatives. So it's an integral of delta phi I dl over d phi I plus delta d mu phi I dl over d mu phi I d for x. Yeah. Now again, we did what we just did with the Lagrangian, the classical Lagrangian, right? We just replace the order of differentiation, and in the second term we have delta d mu phi I. We can write it d mu delta phi I, and integrate by parts. Recalling that the delta phi I on the boundaries are 0, right? So integrate by parts. And we get just like that. So from this part, integral d mu delta phi I dl over d mu phi I delta for x is delta phi I dl over d mu phi I at the boundaries, so I'm just going to call it d omega, minus integral delta phi I d mu dl over d mu phi I d for x. Okay, just did the integration by part of the second term. Right, this is integration over, this is the boundary of the 4 volume, which goes to infinity, so it's equal to 0. That means that if we take all that together, combined, we get that from here. So overall, again, integral. We have this integral of delta s is equal to 0 is integral delta phi I dl over d phi I minus d mu dl over d mu phi I. D for x is equal to 0. And since delta phi I is arbitrarily chosen, yeah, just let me finish. Then we end up with the equivalent, which is the Euler-Lagrange equation, which is dl over d phi I minus d mu dl over d mu phi I is equal to 0. Which is the equivalent of the Euler-Lagrange equation. In fact, if you follow the point, the logic here, it's identical to what you've been doing in classical mechanics. There's this addition of this integral over dqx. That's it. Yes.
When you say d omega, you mean to like surface integral?
Yeah, but omega normally it's a standard term. The differential of a volume right to the omega. Yes.
Why does the integral over all space vanish?
The integral does not vanish. The
d omega part.
What? The delta phi I here vanishes, right? Or yeah, delta phi on the boundary vanishes. So it's infinity. There's no change. Yeah.
The equation is for each mu separately, or you're summing over mu?
No, there's summation over mu.
Okay.
Right. For each phi separately.
Yeah.
Okay. Example. Right? Something which you might have even seen. Did they show you the QFT in one dimension? Right? Or no, sorry, not QFT because there's not quantum. Classical field in one dimension. Classical field in 1D. What is a classical field in 1D? String. Call it string. Didn't they show you that string example in classical mechanics? Some said like that, some said like that. I don't know which to believe.
You didn't teach all of us.
I didn't teach all of you.
Wait.
What? String.
We know string.
Not string theory, just string on
Yeah. Yeah, we know.
You know. It's just an illustration, right? So let's say we have a string. Right? X. Right? For our purpose, this is going to be 5 x and t. Right? And we have some string. It looks like that, right? So the string has a mass per unit length, right? How do we call a mass per? How we denote the mass per unit length? Density, right? So density of a string is a mass per unit dm over dx, basically. Right? And then it has a tension. This is a density. There is a tension which we call tau. So for our calculation, the field will be the transverse displacement. So assuming that phi of x and t is the transverse displacement, namely the displacement in the y direction. So really it's phi x and t, this is just a y, it's a function of x and t. So what is dt phi? Dt phi x and t. What is that? It's the velocity. It's the velocity in the y direction. I'm not sure. Looking at your faces, I don't see such a great happiness. Now, tau is the tension, right? So what is tau during the tension? Then tau dx phi, right? This is just tau tangent theta. Theta is the angle from the x-axis. So let's assume it's a small oscillations. So what's the kinetic energy and the potential energy?
Are we talking about the
Half
density?
Mm-hmm.
half wall velocity square.
Yeah, so T is integral from x1 to x2 of half rho and what?
The T to the phi.
Right.
Squared.
dt phi squared dx. And the potential V is integral from x1 to x2 of tau dx phi times phi dx.
So we need a half. Because it's
Yeah,
not the-
which is half, or integral from x1 to x2 of half tau dx phi squared dx. So the Lagrangian density L with half rho dt phi squared minus half tau dx phi squared, which I can write as 1/2 rho d0 phi squared minus v squared d1 phi squared, where v is just square root of tau over rho. If we put that inside Euler's Lagrange equation, yeah,
Isn't it like dou x phi times phi is dou x of phi squared? And then you need to integrate by parts, so you have a minus or something.
I don't know. Check it out. Check out the algebra, but no, this should be the correct one.
But the
You mean this one?
Yeah.
Yeah, no, that's fine.
But how when you need to, it's dou x of phi squared, not dou x of phi squared.
Go x of phi. Yeah, no, it's okay.
No.
The phi dx times phi is half the phi dx squared. It's okay.
It's dou x of phi
It's
squared.
phi squared dx.
But you do integral by parts, and then maybe why? I mean, you derive phi squared, not, or you doing integral by parts.
I
You
integrate
have
by
a
parts.
minus.
No, it's an integration by
So
parts.
don't you need a minus somewhere?
No. Okay, check it out.
Okay.
I'll check it out myself, but I don't think there's any problem. I don't see the problem at the moment, so just check it out later. Mark it. So,
Wait, the units are
what is the L defined?
but the units are in the same sense.
Why?
Because in the left side you have phi, and like the x of phi is unitless. So in the left side you have phi, which have it's y direction, so it's meter units. In the right side you have only tau here.
No. No, there's no problem with units here, right? You have a v squared. It's the same as a wave equation, essentially.
Okay.
Okay, we'll check it out. What is the L defined? 0. dl d 0 phi.
או D0.
DL D1 phi minus rho B squared D1 phi. And the Euler-Lagrange equation, rho D0 phi minus, rho D0 of D0 phi minus rho D squared D1 phi is equal to 0. Or in language that you're more familiar with, D squared phi over D squared minus V squared D squared phi over dx squared is equal to 0. What did we get? Wave equation, right? This is a standard wave equation in a string. I'm asking you again, did you see that before?
The wave equation? Yeah.
No, this derivation of the wave equation inside the string. Wave equation, I know that.
The wave equation is
The string that's derived from, sometimes you do it in how do you call it, advanced classical mechanics in second year. What?
Analytical mechanics?
Yeah, analytical mechanics, mechanical analytics. Sometimes people do it. No?
ראינו שבגלים, אבל במכניקה ניוטונית, לא
בגלים על סטרינג? אז טוב, אז בגלים. ראיתם את זה?
אבל עם ניוטון לא היה...
כן, לא
ולא עם לגרנג'?
לא.
אוקיי. ניוטון and Lagrange agree. Okay. It's going to be very surprising if Newton's formalisms give you one result and Lagrange formalism typically means you did something wrong. So I got the right result, so I likely did not do anything wrong here, but I'll double check something. Okay, good. So, right. Yes.
מה עשית שם באמצע עם הדו L, דו פסאי, דו פי?
Phi is equal to 0.
למה?
כי L לא תלוי ב-phi. L is only a function of d phi over dt and d phi over dx. It's not a function of phi. When I take a partial derivative of L with respect to phi, I get 0. Okay? But so far so good. What do this question that you have about that? Now let's go. So this is just an example of how to make use of Euler-Lagrange's formalism in the formalism of quantum field theory to derive a result which you already know. This is not a real Lagrangian, right? That we care about. It is a Lagrangian. Lagrangian here represents the Lagrangian for a string, right? But we're not interested in Lagrangians for strings because we're doing particles. Okay, so we have to do Lagrangians for the fields. Let's do it. Can I erase that point? Sure. Erase. You have still a merge. So, what equations did we learn? Basically 4 by now. Klein-Gordon, right? So Klein-Gordon represents a what? Spin 0, scalar, massive scalar field. Right? So spin 0, massive scalar field It's a Klein-Gordon equation. That's for a field we call the phi. That's a standard way of denoting the Klein-Gordon field. Again, this is not a physical field because we don't have a spin zero massive field. Right, so the Lagrangian, forget about the interaction. So Lagrangian for a non-interaction, Lagrangian or a non-interacting field like that. L, I put it with an S. It's gonna be half d mu phi, d mu phi. When there's d mu, there's always one lower, one upper. Minus 1/2 m squared phi squared. That's how the Lagrangian looks. What is d mu phi? D mu phi? What is that? dt phi and
minus
sum over I equal 1 to 3, right? di phi squared. So, dl d phi
minus m squared.
Yeah? Yeah? Phi. dl d0 phi. What?
D0.
Right, d0 phi, which is also d0 phi, doesn't matter. dl di phi. What? Minus di phi, which is equal to, if I'm going to raise the index, plus, right? So it's a plus di phi. Yeah? To say yes. If there was an exam, I would check exactly what is the yes means. Euler-Lagrange equation, which is a question of motion. From here, right? Euler-Lagrange. What do we get? Minus m squared phi. Right? Minus what? What do we have? No. D0 squared phi
minus
blah blah phi is equal to 0, which you can write as what?
Is it the Laplacian?
It could be, right? But I'll just write it as d mu phi.
I start with why is it Laplacian, not Laplace? Or it's
di Laplace squared is Laplace squared. Laplace squared.
okay. The vectoric Laplace.
Yeah, Laplace squared. Laplacian squared. d mu phi plus m squared phi is equal to 0. Right? Bingo. What is that? This is a Klein-Gordon. Right? What is this term here? How do we call this? This is the kinetic term, right? This is the kinetic energy. This is the kinetic term. And what is that? What do we call that? Yeah. Let's call the mass term. right? Everybody sees that? Yeah? Cool, isn't it? Everything like that. Say like it's very easy. You don't know what I'm talking about. Questions? Wait until we get to the interactions. This is Lagrangian for a free particle. Right? There's no interaction, it's just the particle itself. Because Klein-Gordon represents a free particle. What about spin half field? Still free. Dirac, right? So I can erase that? I was hoping to do the interactions today. But spin half. Still free field. Relativistic. Not free. Yeah.
You said that this is the Lagrangian of free particles singular or free particles of the same type?
Of the same type, but they are all spin zero. Right. Klein-Gordon represents a field which represents spin zero relativistic.
Multiple particles or one particle?
Well, phi is a field. Yeah. The concept in quantum field theory is that a field can generate multiple particles. It's a matter of excitation. Right? It represents a particle of one type.
Yeah.
And so the field phi in the Klein-Gordon equation represents a spin zero massive particle. That's it. If I use this field on the vacuum, I can excite as many particles as I want of the same type. There is no interaction in this Lagrangian. So this, when I write down this Lagrangian, that means that I am in a theory, in a model that allows the existence of such particles, but they don't do anything interesting because they don't interact. Okay? So there can be multiple such particles, but it's kind of boring because they just can be there or cannot be there, but I don't care because they don't do anything interesting. Okay? Right. It's fine? Spin half. Obviously we have Dirac. Anybody want to guess how the Dirac Lagrangian would look like? Dirac. Just write it down. It's a psi bar I gamma mu d mu minus m psi. What is psi? Yes, this is, how many free parameters does the psi have? 8. Right? Why 8? It's complex, right? It's complex for variables. So we have 4 plus 4 basically, and it's a complex. So Dirac spinor psi composed of 8 independent real fields. Real fields. And I can use all 8 as generalized coordinates. Okay? All can be used as generalized coordinates. I suggest that you take half an hour, go and make sure that you understand the difference between standard coordinates and generalized coordinates. Okay? Give yourself an example, the differences. Now, we can use them, but obviously it's more convenient to take some sort of some linear combination of them. Which one am I going to use? The the four components of psi and psi bar. Right? It's going to be a linear combination. However, it is more convenient to use a linear combination and take the four components of psi and psi bar. It means that we have to take partial derivatives, right, independently with respect to each of the components of psi and psi bar. Okay? So, let's see. If we take psi bar, what is dl Dirac over d psi bar?
I gamma m dot m minus m all
I gamma mu dot mu minus m mu, right? No m. Minus mu d mu psi minus m psi. Dl Dirac over d mu psi bar.
Zero.
Is a what?
Zero.
0, right? And when we plug that into the Euler-Lagrange equation, yeah, exactly. So when we plug it into Euler-Lagrange equation, we get the Dirac equation. I gamma mu d mu minus m psi is equal to 0. That means that it's cool, right? Now, what about taking the partial derivative with respect to psi? So dl d over d psi, what do we get? Minus m psi bar. We'll switch the order because m is a scalar. And dl Dirac over d mu psi.
I
We get
I gamma mu psi.
what?
I gamma
Yeah, I psi bar gamma mu. Right. Now I have to be careful. So what are we going to get? These two?
It's this to give mu in the lower side because so
You
the
can
index is
switch against the minus.
Right? So I get the minus m psi bar. Right? Minus I gamma mu. That's right. Minus I. D mu psi bar gamma mu is equal to 0. So it's also a correct equation. Right? This is the Dirac equation. The second equation, which can be directly obtained from the Dirac equation, really, but it's can be obtained here as well. So again, we have two terms here. So we have the term which is what? Minus m psi bar psi. That is what?
Mass.
This is the mass term. Right? This is the mass.
with or without the minus?
Normally with the minus. And then we have a psi bar I gamma mu d mu psi, which is what?
Kinetic.
This is the kinetic term. Kinetic term. Yeah? All these terms appear. This term does appear in the standard model Lagrange. Lagrangian. As opposed to the Klein-Gordon, which does not appear. This does appear. More? It's the first time we're introducing a term that actually appears in the standard model.
אסף,
Yeah.
כתבת שם, כאילו מחקת את זה, אבל אתה יכול להשתמש בצירוף ליניארי.
נכון.
זה מתבטא.
זה שבמקום להשתמש בשמונה, השתמשתי בפסאי ופסאי בר. Rather than use, I could make use of real parts of psi versus imaginary parts of psi. Rather, I'm using psi and psi bar. Mathematically, it's the same. Physically, I get physical insight. More questions? I'm always optimistic about how much you can do in class. These things take time. Am I going too fast, by the way? Am I going too slow? People don't complain if I'm going too slow. Never. Okay, let's see what else do we have. So these were scalar fields. What about the vector fields? Relativistic. Switch back to that. Relativistic vector field. Hey. Right, remember the relativistic version of Maxwell's equation, right? For the electromagnetic field, we had what? D mu, F mu nu is J nu. This is the relativistic version of Maxwell's equation for the electromagnetic field right, remember that F mu nu was D mu A nu minus D mu A nu. And remember also that I told you that this definition changes between different textbooks.
And then I.
What?
I is for the equation, is the
This is the equation.
smaller than mu actually. The I or the
No, the cosine. What will be Lagrangian? The electromagnetic Lagrangian, LEM. That you might have seen in your. Did anybody take like fields course? Electromagnetic fields? Yeah. Did they show you the electromagnetic Lagrangian? Sometimes they did. Often I think not, but sometimes people show that. Minus 1/4 F mu nu F mu nu. Does that look familiar? No? Yes. First time you see that? Yes? Who saw that? You saw that, yes, I know.
I saw it in pictures of the standard model.
So the picture of the standard model. Okay. Minus J mu A mu. Right? So you see that I'm not lying, right? It is there. We're starting to get into terms that actually appear there. Okay, so this is the Lagrangian of the electromagnetic field. And if we do the Euler-Lagrangian equation of motion, what do we get back? Right. Of course, we get back maximum.
How many degrees of freedom are there? The A?
4. Right. A mu is a 4. Yeah.
Real 4 vector?
No, we said that we have 2 degrees which are degenerated, so there's really only 2 degrees of freedom there.
And they're real?
Yes, you have which essentially we showed that, we talked about it. It will describe polarization of the vector. These are real. Photons can be polarized in 2 ways. Okay, so Euler-Lagrange gives back Maxwell. What about the massive vector field? We discussed that. Roca. So, massive vector field, we have L Roca is minus 1/4 F mu nu plus 1/2 m squared a mu. Then the Euler-Lagrange gives back the Roca, which is the Lambertian plus m squared of a mu is equal to 0. It's impossible to see. It's a Roca equation. Okay, I'm not spending more time on that because I want to get to the. Okay, it is cool if you haven't seen it, but now there are the cooler things are now coming. Questions about that?
Why is there no J in Roca?
I don't know because there is no.
No source term?
No. Yeah, exactly. You have a particle already in there. There's no source. I hope I didn't confuse anything. Okay. More? Mm-hmm. Yeah. No. I meant more questions, but okay. Okay, so now, before we're going to start dealing with interactions, which is where I'm aiming at, a short detour, but very important. Netter's theorem. I'm sure you've heard about that, right? Did anybody show you the derivation of Netter's theorem?
Yes.
Yes, good. Where?
Analytic.
Really? Yes. Typically, it's not done in analytical mechanics. Okay, it's a good, interesting surprise. Normally, this is done at a different level. But okay, good that you saw that.
ראינו גם דברים דומים לזה, פשוט במשפט שראינו.
בסדר. מי הראה לכם את זה?
אבי.
מי? אבי. יפה. לא אמורים להראות את זה בדרך כלל.
רוקה הוא לא הראה.
לא, לא יש פה.
לא שום סיבה להראות את זה. גם את גירה כולו הראה לכם.
אתה טרנז'יאן ששראיתם כאילו.
זה לא הראה לכם? לכן יש שנים.
סייד צמוד.
איך זה קשור למכניקה אנלית? גרעין סבבה, זה קשור למכניקה אנלית. בסדר, יפה, הגדיל ראש.
אמר שזה אפילו היה שאלת מבחן.
מה?
אמר שזה אפילו היה שאלת מבחן.
לא, הגדיל ראש, זה לא אמור להיות חומר קלאסי של מכניקה אנלית. טוב, Netter's theorem. What is Netter's theorem? Right, Netter is aiming Netter, right? Everybody knows. Einstein was a big fan of her. What is Netter's theorem saying?
The symmetries correspond to a conserved quantity.
Yes.
And vice versa.
Continuous symmetry. Okay, we spoke about A, we spoke about discrete symmetries. So Netter's theorem basically states that for every continuous symmetry of the Lagrangian, something is right, which is a bit difficult to find right now. Every continuous symmetry of the Lagrangian gives rise to a conserved current J mu of x. It's a slightly different version of what you've seen in classical mechanics. J mu of x, such that the equation of motion implies that this is conserved. D mu J mu is equal to 0. There is always something conserved. I'm not going to prove it for you right now. It's actually not a very difficult proof, but I'm not going to do it right now. Example, right? Which is, I'm sure if you've seen that, you've known it, right? So, example. Particle M moves in a gravitational potential. Right? Particle M. It's a classical example. Yeah? Particle M moves in the gravitational potential of M, larger particle. Right? Fixed body. What's the Lagrangian? That's a classical. T minus V. There's a what? What? Half M G squared plus G M divided by R. So, if we switch to polar coordinates, that's going to be half M R dot squared plus half M R squared phi dot squared. This is not a field, this is a polar coordinate phi. Plus G M divided by R. R phi polar coordinates. What the Lagrangian does not depend on? Phi, right? L does not depend on phi, right? Which means what? That if we make a transformation from phi to phi prime, which is phi plus delta phi, what happens to the Lagrangian? Nothing, right? It's nothing. So, corresponding Euler-Lagrange equation, d over dt of dl over d phi dot is equal to 0. That's Euler-Lagrange. That means a what? What is the conserved current? What? J from here. J is dl d phi dot. dl over d phi dot, which is r squared phi dot is the conserved current. Conserved current. Which is of course the angular momentum. Okay, but not with this formalism. This is, for me, this is a current. Okay, is that clear? Can we jump deeper into the water now? Yes. Okay, good. So this will take a few minutes of your time. You ready to spend another? Well, we started 5 minutes late because of this one. It's okay. I'm gonna take another 10 minutes of your time. Let's start with the global symmetry. That's not what I aim at. I'm aiming at global symmetries. But let's start with global symmetries. This is a global symmetry. Yeah.
Why is the derivative equal to 0?
Euler-Lagrange. Just write down Euler-Lagrange equation. That's all. Because there is no phi dependence of L. You have the L d phi, the d over dt, the L d phi. That's all.
Wait, now how is it from U to J? How does this, because this is a scalar, so how?
I got the L d over dt, the L over d phi dot is equal to 0.
Yeah, but J is supposed to be a current, but it's one of
J
J
phi.
is supposed
You
to
want
be
it
a
in
four
phi.
vector. Ah,
It's a phi direction. Q1 symmetry and conservation of electromagnetic charge. Okay. But write down Dirac-Lagrangian. L Dirac, psi bar, I gamma mu d mu minus m psi. Now, this is invariant under a global transformation of the fields. Invariant under global transformation of the field psi. Namely, global is important, global phase transformation. What does it mean? Global phase transformation means that psi of x could go to psi prime of x, which is E I Q chi psi of x, which is also U chi psi.
this guy.
The real question is, what is Q? Chi is an arbitrary parameter, real parameter. Chi, real parameter. Arbitrary value with arbitrary value. Now chi is a constant, namely it's independent in space and time. That's what I mean by global symmetry. Okay? If it was local, it would be a function of space or time. And now it's a global. Q is also a real constant, which in principle I don't really need it here, but it's for future purposes, as we say, right? Which is going to be the electric charge. Q is a real constant. Here is the claim, right? I'm going to use Noether's theorem. I'm going to show you that the fact that Dirac-Lagrangian is invariant under global phase transformation of the field means that there is conserved quantity, as we just showed. This is Noether's theorem. And that conserved quantity for this specific symmetry is the charge. That means that the charge is conserved. Yes.
What do you mean by psi tag? Which
I changed. I transformed the field. Now it's a different field.
What transformation happened?
This is the transformation I made. Right? Like before that, for example, I transformed in space. I moved from phi to, when we talk about the classical Lagrangian of a particle in a gravitational potential, right? I made a transformation, right? This is the sun, this is the particle that rotates. So okay, this is phi, and now I move here, right? This is phi prime, which is phi plus. That was clear? I made a transformation and the Lagrangian did not change. So we are making also a transformation. This is now, it's called the U1 symmetry. Right? It's a phase transformation. I'm building up a phase. Okay? That's why I have the e to the power I q kind of. Okay, I'm building up a phase, and I'm arguing that the Dirac-Lagrangian is invariant under this phase transformation. Global phase transformation. And my second argument is that this is going to give rise, according to Netter's theorem, to a conserved quantity, which is going to be the charge. That's what I'm going to prove to you. And the third argument, which I'm not going to prove it today because we're already out of time, is that all the interaction and all the conservation are derived from these symmetries. They're totally extremely cool. Not just cool, it's extremely cool. How it works. So we make it to this transformation. What happens to the Dirac-Lagrangian? So L Dirac, which was psi bar I gamma mu d mu minus m psi, is now transformed. So this is U, capital U. Make sure you're all aligned. Capital U is now what? Psi bar. What do I have to add? U star. Right? I gamma mu d mu minus m u psi. Right? But what is u? It's just a number. Because everything is constant. Right? It's a real parameter. It's independent on the space or anything. Right? It's just a number. So u star u will give me 1, right? So this is just equal to LD. Nothing here, right? Right. So U commutes with everything here, so I can just take it. Now we said, according to Netter's theorem, this is a continuous transformation, so there must be a conserved current. Let's look at the current. So according to Netter's theorem, there is a conserved current. Okay. Changing the Lagrangian, delta L Dirac is dl d psi delta psi plus dl d mu psi delta d mu psi plus dl d psi bar delta psi bar plus dl over d mu psi bar delta d mu psi bar is equal to 0. Why? Because the Lagrangian is invariant. Right? Because Lagrangian is invariant, then I make a small change in the Lagrangian, I get a 0. Right? Because LB is invariant. Now to make things easy on me, I'm going to assume delta psi is small. Right? So there's a small change. So if there's a small change, right, then I can use Taylor expansion to a first order. Right? What we have? E to the I q chi is equal to what? 1 plus I q chi. Right? So what is delta psi? What is delta psi? What is delta psi? I q chi psi. Right? This is delta psi. Psi bar, psi prime minus psi. Right? Delta psi is psi prime minus psi. That's delta psi. Yeah?
Yes.
Similarly, delta of d mu psi is I q chi d mu psi. Delta psi bar is minus I q chi psi bar, and delta d mu psi bar is minus I q chi d mu psi bar. Using this in here, we get delta L Dirac is I q chi. I just remove the Dirac, so just the L over d psi plus dl d mu psi minus I q chi psi bar dl over d psi bar plus d mu psi bar dl over d mu psi bar. And that is equal to 0. Now, the term is the derivatives. Again, I'm repeating the same stuff that I've been doing here already 3 times. I'm doing the same thing here. It's a different pen because I want to make sure that you actually see what I write. So, dl, I want to see d mu psi is d mu dl d mu psi minus d mu dl over d mu psi, and the same for the d mu psi bar. Okay, completely standard. And then we have delta L is I q chi dl d psi minus d mu dl over d mu psi plus d mu dl d mu psi minus I q chi psi bar dl d psi minus d mu dl over d mu psi bar plus d mu psi bar dl over d mu psi bar. And that is equal to 0. Again, nothing fancy here. It just looks a bit ugly, but there's nothing really here. Yes?
Where does the first purple line come from?
Here. It's the same thing here.
No, not this one. The first purple line.
This one?
Yes.
Oh, I just opened up. I just expanded the derivative. That's all. A prime b, right, is a times b prime minus a b prime. That's all. Now, these two cancel by the Euler-Lagrange equation. This is cancelled by the Euler-Lagrange equation. So what we are left with only these two. Now the chi I can remove, I don't need it anymore. So I have the Q dl to d mu psi d mu of that minus Q d mu d psi bar dl over d mu psi bar is equal to 0. And remember the derivatives that we had previously that we calculated. dl over d mu psi bar is equal to 0, and dl d mu psi is I psi bar gamma mu, which we derived. Use these terms. And we get that d mu q I psi bar gamma mu psi is equal to 0. Which means that the conserved current according to Netter is J mu, which is Q I psi bar gamma mu psi.
Seth, you need to change marker.
I know. You need to throw away all these markers and go to the secretary and get new ones.
It's hard to distinguish what's written on the right side.
I psi bar gamma mu psi. This is the conserved Netter's current. Yes. Question?
What is written on the top right? Hard to distinguish.
Q d mu. These two terms cancel because of Euler-Lagrange. So I'm really writing these two terms. That's what I'm left with. Okay, I have these two terms, Q dl over d mu psi minus Q d mu psi bar dl over d mu psi bar is equal to 0. Yes.
לא יכולת להשתמש בשביל למצוא את הזרם בביטוי של הזרם שהוא תלוי ברקע השנייה?
Yeah, it's the same. This is the same current that we got previously, but we derive it using Netter's theorem now.
איפה השתמשת אבל
במה? Delta LD is equal to 0.
במשפט של...
אה?
איפה השתמשת באמת?
כל מה שהוא עשה.
Everything in it. I equate A to 0. I equate A to 0, and then I search for the conserved Netter's current. Is conserved is what we get when we use Netter's theorem for a global U1 symmetry. Right? We add up a global phase. Right? We take psi, we add up a global phase, we multiply it by U, right? And we discover that this gives rise to that specific current. Okay? So, what we did, let me write down because that's the bottom line, that's the most important thing to remember from this mathematical manipulation that we did. What we did. So, we formed Dirac-Spinor using U, which is a 1-by-1 matrix, unitary matrix, 1-by-1 unitary matrix. It's really called U1 symmetry group. It's a technical term if you learned group theory. Let's say you want symmetry group. We'll see more if you get like that, but that's going to be next lecture. And we discovered that there is a conserved current, which is Nutter's current. So we found the conserved Nutter's current, from which we have a conserved charge. Q. Let's see why I put this Q there. So we say in math lingo, we say that the conservation of charge follows from invariance of the Lagrangian under the group U1. Conservation of charge follows from the invariance of the Lagrangian under the group U1. Yes.
But when you introduced the current Q, you said that Q is a constant.
Q is constant.
So,
Q is the charge. It's constant.
so you already knew that it's
Yeah. That was a small demonstration, which we're going to continue on Thursday, to see what happens when the symmetry is local, not global. Then chi is going to be a function of space and time, and the free factor, if be Q or something else, would be another constant. So that is to be discussed on Thursday. Now I know we already go very late. I'm sorry that it took more than I thought, but it didn't seem to be too bad. You seem to be quite happy, and I'm telling you, we're just getting to the fun part, so it's a pity that the semester is going to end so quickly. Yeah. More questions? So, excuse me again for taking too long of this lecture, and I'll see you all on Thursday to continue with exactly the same line of reasoning. So use these 2 days if you're not fully familiar with what's going on here, because these are new stuff for you. Sure about that.